Robotics, Heuristics-based singularity-free. Inverse kinematics and Jacobian inverse. Abstract in robotics, inversion is encountered at two levels, inverse kinematics level and inverse Jacobian level. We present a new and intuitive approach to simplify the existing analytical complex approaches for inversion, kinematics and Jacobian. Inverse kinematics also employs geometric approach. We present a different style to efficient geometric approach. We show that specification of end-effector position is not necessary. Robotic Jacobian is an M times n matrix with n degrees of freedom, DOF. The computation of inverse velocities is an issue when n, for which we provide an intuitive and common sense approach to the generalized inverse. Thus, this paper provides intuitive exciting approaches for efficient computing of inverse kinematics and inverse Jacobian in robotics. Keywords, link parameters, inverse kinematics, inverse Jacobian, generalized inverse, degrees of freedom, DOF. Introduction. A robot is a rigid body composed of links and joints on links for motion, see Fig 1, Fig 2. Kinematics is the study of motion without regard to the forces that create it. The representation of the position of the robot end effector through the robotics engineering, common parameters and link, forward kinematics 1, 2, 3. Forward kinematics yields a unique orientation and position of end effector, but the end effector may be reached in multiple ways. There can be several paths for a robot to reach a destination. If the link parameters for joints are specified, forward kinematics uses these joint parameter values to reach a unique destination. Inverse kinematics of robotic manipulator involves obtaining the required values manipulator joint position given the desired endpoint and direction. There is no unique solution and close the form of direct expression of inverse kinematics mapping 2, 3, 4. However, if the orientation and position of end effector is specified, then inverse kinematics determines possible link parameter values that may result in multiple solutions, some of which may be extraneous and inconsistent. Inverse kinematics employs a bag of heuristics using one trigonometric equation and avoiding division by zero singularities. This analysis explores the multiple solutions and exploits the valid solutions. We will devise common sense approach. For inverse kinematics in geometric approach, to reach intermediate frames, it is computationally efficient to start from base origin see Fig 5, Fig 6 instead starting from end effector. It is also intuitive to grasp. Here we provide a heuristic approach to solve the required equations. Also, inverse kinematics employs geometric approach to break down the 6 DOF into 3 plus 3 see Fig 5 or 4 plus 2 see Fig 6 etc. Motion occurs about or along the axis at the joints where frames are specified or computed. Multiple solution issue with Jacobians is resolved by using minimum norm criteria. In practice, a robot has 6 DOF, articulate robot may have all revolute links. For a robot with 6 DOF, normally arm has 3 links and wrist has 3 links. Some robots may have 2 to any number of links. In any case, in general, the number of links may not be equal to 6, 5. As in forward kinematics, application of forward velocity is also straightforward. In fact, this becomes an issue only when the Jacobian is not a square matrix. It happens when the system of equations is underdetermined or overdetermined. For this inverse Jacobian problem, there are algebraic approaches to resolve this 2,3. We provide more efficient ways to grasp the concepts of inverse kinematics and inverse Jacobian. The paper is organized as follows: Section 2 is overview of background, Section 3 describes innovative techniques for computing inverse kinematics, Section 4 is on geometric inverse kinematics, efficiency, Section V is intuitive inverse Jacobian, Section 6 is conclusion followed by references. 2. Overview of background. A robot is a rigid body composed of links moving around a joint axis. The link parameters are .k, dk, ak, relative to link 1, are used to determine a coordinate system, the link frame. The link frame ek is computed by starting at the origin of frame ek1 in 4 transformations: 1. Rotate about zk1 axis by angle .k, translate along zk1 axis by amount dk, translate along xk axis by amount k, and rotate about xk axis by angle k. The composition of these 4 transformations called an A matrix or coordinate frame. The A matrix is akin to transformation from one frame to next frame. The frame for transformation from frame K1 to frame K becomes A attribute matrix, synonymous with transformation matrix T, or the frame matrix F. For notation, K1AK represents transformation from frame K1 to frame K equivalently, it is frame k relative to frame k1. For notation, the symbol 0rk is the rotational part of the matrix, onk, ok, ok, are unit vectors forming a right-handed system of orthogonal vectors. This represents the orientation of frame ek with respect to base, and 0pk is the position of the end effector with respect to the base frame. Inverse kinematics and velocity are described briefly as: forward kinematics is a chain of frames or a matrices k1 ak for k equals 1n, resulting in On. In order to have complete and simple solution to inverse kinematics for robot manipulators, it is solved analytically to determine closed form solution. Inverse kinematics determines the chain of frames or a matrices k1 ak for k equals 1n from the end effector, On. Inverse kinematics is based on a standard trigonometric equation a cos, dot, plus b sin, dot, equals c with c2 equals, a 2 plus b2. Its solution is devoid of singularities of division by 0. For velocity, the velocity equation uses the Jacobian, j, t equals j, 5. Forward Jacobian, velocities, at the joints are specified, the problem is to find end effector velocity, t. Inverse Jacobian, the end effector velocity, t is given, the problem is to find link velocities, at the joints. 3 techniques for computing inverse kinematics. The inverse kinematics involves solving trigonometric equations. If such equation is not solved properly, it may lead to divide by 0 singularities in the solution 3. For example, in the case of a 6-link robot with first 3 links create the arm, we will first solve the arm before we go into full-scale 6 links. For the sake of completeness, we include the robot Fig 2, link parameter table Table 1, and the A matrices, etc. For example, jumbo drilling robot is displayed here in Fig 2. The Fig 2 has clearly marked joint axes and link parameters. One may flatten the robot, see Fig 3 to set it in the rest position for ease in creation the link parameter Table 1. A forward kinematics. In forward kinematics, we multiply these 3 A matrices, use trigonometry to combine complex expressions into simpler ones. There is a unique solution for the end effector orientation r and position p, see equation 6. The end effector presentation uses the simple notation for cosines and sines, sk equals sin, dot k, ck equals cos, dot k, and we have. The first 3 columns form a right-handed system of mutually orthogonal unit vectors of the rotation matrix, and the 4th column is the position vector. Be detour to trigonometry. Inverse kinematics depends on the ability to solve trigonometric equations. Basically, 5 trigonometric equations were required to solve the inverse kinematics problems 8. It is not necessary to solve 5 different equations. Only one trigonometric equation is sufficient to resolve all cases. Any special case follows from the same equation. Consequently, in robotics, inverse kinematics amounts to solving the trigonometric equation a cos plus b sin equals c. 7. All other cases involving trigonometric functions are special case of this equation. A cos plus b sin equals c, c2 a 2 plus b2, 8. The joint mobility is constrained by mechanical limitations or physical stops. Each joint limits are tied to prismatic and revolute joint that are valid irrespective of the configuration of the remaining links. There are 3 trigonometric functions, sin, cos, tan. The inverse function sin1, value, tan1, value, determine angle between 2 and 2, whereas cos1, value, angle is between 0 to. For robots, the rotation angle for the arm joints is 270 degrees and the wrist joints is 180 degrees. Fig 4, 360 degree for drilling hole 2. The sin1, value, cos1, value, tan1, value, are insufficient to cover all quadrants for accuracy. Some authors use the inverse functions erroneously 9, 10. For example, we explore solving the following equations for point 1, point 2, d3, from the position 6 of robot arm. Their 10 method would solve them as follows. Their approach runs into undefined values for point 1, point 2 on using standard inverse atom functions. There are several issues with this calculation. 1. Cancelling negative sign creates discrepancy of 180 degrees in the angle. 2. Cancelling, S2D3A1, is not practical if it is 0. In that case division by 0 is undefined. That is, if equals 0, then point 1 is undefined. In fact it may be well defined. We propose to use ATN2, tan inverse with two parameters, if px equals 0, pi.0, then, which is again undefined if the expression, a1c1px s1 equals 0. It leads to both point 1 and point 2 as undefined as well as erroneous. In fact, the solution can be well defined if we avert any such discrepancies involving divisions by 0 that create undefined expressions. First, we use ATN2 function that prevents such discrepancies of undefined terms in the calculation of angles. Second, we avoid divisions by 0 as follows. In general, using ATN2, the solution of C inverse kinematics analytical. With trigonometry at hand, we are in a position to solve the three-link inverse kinematics for the end-effector. Depending on the robot, the inverse kinematics problem may be specified with just a. Orientation of end-effector, 2. Position of end-effector, or c. Both the position and orientation of the end-effector. C.1 Inverse kinematics when only end-effector position is specified. If the position alone is specified, there can be multiple solutions. Let the postgen P be provided for this example. For geometric approach to inverse kinematics. Here we provided an efficient way to solve inverse kinematics and inverse Jacobian problem. We determine the intermediate frame at the end of arm, link 3 or link 4 between the base frame and end effector of a 6-link robot. It makes it easy to solve 3-link or 4-link inverse kinematic problem. For larger number of links, it becomes more challenging. To overcome this complexity, sometimes geometric approach is used. 6-link robot inverse kinematics problem can be easily solved by partitioning it into 3 plus 3 fig 5 or 4 plus 2 fig 6-link inverse kinematics problems. The traditional geometric approaches require the specification, with respect to base, of both position and orientation of the end effector, 0001. Now with NOAP geometry is used to calculate, with respect to base, 0001 for the end of link 3 or link 4. Using 0001, we calculate the parameters of first 3 or 4 links. Once it is done, we solve for parameters of the remaining links by equating frame 3 or frame 4, product of remaining matrices, respectively to 0001-1, 0001. We propose to require only orientation of the end effector, that is sufficient. Specification of the position of end effector is not necessary. See Fig 5, 6 for 3 plus 3 and 4 plus 2 partitioning. In either case, we need these parameters at the end of 3 or 4 links. Fig 5, 6. Once the frame at the end of arm is determined, it can be used to solve the rest of the problem, as we saw in analytical solutions above. The orientation and position of link 3 or 4 can be determined without the position specification of the end effector. All other steps are similar to previous paragraph. More details on comparison of two approaches follow. A traditional approach. In Fig 5, 3 plus 3 case, visually the orientation of frame 3 is the same as frame 6, so the frame 3 orientation is the same as specified for the end effector. Standard approach to get the position of frame 3 with respect to base is as follows. Starting from P, we can go a 4 units in direction n, a 6 units along n, it gives the a 4 plus a 6, along n and d6 along a. This means P plus, a 4 plus a 6, n plus d6a equals P, which is given. Therefore the position of frame 3 origin is P equals P, a 4 plus a 6, and d6a, completely known in terms of base coordinate system. In Figure 6, 4 plus 2 case, visually the orientation of frame 4 is such that n is the same as n, a is o is a. Standard approach get the position of frame 4 with respect to base frame is as follows. Starting from P, we can go a 6 units along the direction n, and d6 along a. This means P plus a 6 n plus d6a equals P, which is given. Therefore the position of frame 4 origin is P equals P, a 6 n d6a. Be more explanation on new approach. We propose that specification of P is not necessary. P can be directly determined without the knowledge of P. It is observed that NOA is known, base frame orientation becomes NA, O, Fig 5, Fig 6. In Fig 5, we can step a 1 units along n, d3 along O resulting in P equals a 1 n plus d3 O. In Fig 6, we can step a 1 along n, d3 along O, a 4 along n resulting P equals, a 1 plus a 4, n plus d3o. In both the cases see Figure 5 and 6, we have determined that the position is P equals a 1 n plus d3o, orientation is n, O, a equals n, O, A in Fig 5 and the position is P equals, A1 plus A4, N plus D3 O, orientation is N, O, A equals N, A, O in Fig 6. This shows that arm position P can be constructed without specifying P. V. Heuristic approach and justification for inverse Jacobian. The paper presents a heuristic method to solve inverse Jacobian for arbitrary number of degrees of freedom, DOF, robot. The Jacobian inverse computation takes long time, whereas first matrices must be multiplied, then inverse of the product is computed and then inverse is multiplied with the transpose of the original to derive the generalized inverse. We will show how this is simpler and will apply this approach to both under and over determined systems of velocity equations. We also provide a better method for solving inverse Jacobian problems that avoid singularity in the solutions. For Mn or Mn we compute product of A with its transpose in such way that the product is a square matrix of smaller order. For example, if Mn, then ATA is order n times n, and if Mn, then AAT is smaller order m times m. Then we use the inverse of these matrices to arrive at the solution. Without going through the exercise of minimization, we can determine the solution. Vector differentiation is not trivial, used for computing generalized inverses when Mn and Mn. Moreover, for m times n matrix A with Mn, since ATA is a smaller square n times n matrix, inverse is also square n times n matrix. To derive the solution, we simply multiply n times n matrix, ATA, dash 1 and n times m matrix at, then n times m matrix, ATA, dash 1 at and m times 1 vector B in. For efficiently, we can multiply n times m matrix at and m times 1 vector B first, then resulting m times 1 vector ATB, and n times n. Now we compare the computing effort in solving the equations if at is multiplied with ATA, dash 1 first or when at is multiplied to B first. In the case of Mn, inversion is the same in both the cases, the number of multiplications is. First case, 46m, n2 plus, m plus 1, n, m, n2 plus, n plus 1, n. Second case, 47m, n2 plus 2n. Clearly second approach is more efficient. Since we are interested in minimum error or minimum norm solution, we will create the solution directly. Heuristically, minimal error is achieved by using a matrix of smaller dimension for inversion. Smaller the matrix, smaller the error in computation and representation. It also leads to conceptually comprehensible and easy to grasp the solution. A underdetermined system, Mn. For underdetermined systems there can be infinitely many solutions with no error of computation. However, we are interested in solution with smallest norm, in other words, a solution that is closest to the origin or a shortest distance from the origin. Which is the solution to the equation Ax equals b. This solution can be directly and quickly determined from the equation, Ax equals b. For the purpose of creating a smaller size matrix for inversion, let us write. 6. Conclusion. Inverse kinematics and inverse Jacobian are two of the problems in robot motion consideration. We have shown how to resolve these two issues with an intuitive, persuasive, and provable approach. We gave closed form, efficient solution for both inverse kinematics and inverse Jacobians. In fact, we have proved that our approach is accurate and efficient. We hope that the designers will find it useful in understanding and retaining the description for reference in their future implementations.